Hi, Luke here from the Bacalhau project. I'm going to give you a demo of some of the scaling and performance testing work that we're doing on the Bacalhau network. Um, we had a goal to hit 1,000 nodes in a test net in July, and we are very close to that. We are at 750 nodes, although with some significant performance problems at 750. And we have a whole set of work planned in August around improving the performance of large clusters. So this lays the groundwork for those. So I'll start by showing you where the system is at sort of 60 nodes and show you a quick demo of that. And then I'll show you how it's behaving when we scale up to 750. So the first thing I wanted to share is a new visualization tool that we've developed for visualizing the graph of nodes as they're spinning up. And so what I can do to begin with is I'll show you what it looks like for a 20-node cluster to boot up. So you can see we start with this kind of mesh network of nodes. They start out in a star formation, and then quickly the peer exchange algorithm in libp2p kicks in and forms a more fully connected mesh. Let me see what happens if I do this. Oh no, it stays the same size. Okay, fine. And then what we can do, so that's on one physical machine. These are some chunky servers I've got in a small data center in my basement. Each server's got 48 cores and 64 gigs of RAM. And you can see that Bacalhau, this Bacalhau instance, the dev stack is barely using any CPU and memory. It's not even showing up at the top of the list when we just run 20 nodes. So what we can do is we can grab that and then we can peer a second set of nodes to that first set. There we go. And then we can see what happens when a second bunch of nodes show up and connect to the network. You can see they were initially in that sort of star formation, with one node at the center, and then they quickly paired with other nodes in the network, the first set of nodes in the network, and each other using that peer exchange mechanism. So we've got a cluster that looks a bit like that right now. And then I can add a third set of nodes by pairing it with that same random node I picked from the first set of nodes. And then you can see how it looks when the next set of nodes connect. See, they're kind of forming a mesh with the other 40. So now we've got a Bacalhau cluster of 40 nodes and 60 nodes, sorry, and we can run some stress testing against them. So first, let's just run a single job, and we can see how long it takes to submit a single job with parallelism 3. So this submit.sh, it just does a Docker run of busybox bin true with concurrency set to 3. Let's see how long that takes on this network. It takes 500 milliseconds to schedule 3 executions on that network and then report the results. Of course, Bacalhau also supports specifying input data, writing outputs to IPFS, all of those good things. I also just want to show you the Bacalhau describe command, which has improved recently. So you can do describe, and it will tell you the state of the execution on all of the nodes. In this case, you can see which nodes actually did the work and got job results. 1, 2, 3 of them. And you can also see kind of the history, the story of this job. It was created, and then the following nodes bid on it, and then one of the bids was accepted, Most of the bids were rejected. Then the work was completed 3 times, and you got the job results. So this is super valuable kind of visibility into the behavior of the running system that we've added to Bacalhau Describe. Okay, so we can run 3 Docker containers across this network of 60 nodes in 500 milliseconds. Let's test that again, 500 milliseconds. We can run this explode.sh script, which is named explode because it's meant to break things. And it will run in parallel a bunch of executions on the network. At the moment, the parallelism is just set to 2, but it's a good test of when you start putting the system under load, do these numbers go up a lot, or do they manage to stick around where they started? And so you can see with, I think, yeah, this setting, let's have a look. If we look at, if we look in the benchmark folder, and we watch Python 3 result, what is it? Watch Python 3 pars.py, then yeah, you can see in this configuration we're rapidly getting through running lots of jobs, and all of the exit codes are 0, and each job is taking about 600 milliseconds. And that's nice. Those are actual Docker executions that are taking 600 milliseconds each. The batch size is 10, which means it's doing 10 jobs in each run, and the concurrency is 2 in this setting, which means we're only running 2 lots of 10 in parallel at any one time. But just 10 and 2 has been enough to stress these large clusters for reasons I'll go into in a minute. So yeah, 60 nodes, perfectly happy. It is using a bit more CPU and memory on the machines, but it's not completely crazy. The memory is still low, 3.8% memory, 2.4% of the memory, 3.8% of the memory on these machines. The CPUs are warming up, but they're not saturated. However, if remember, the goal of this month was to get to 1,000 nodes. We didn't quite make 1,000, but we've made 750. So let me show you what the system looks like at 750 nodes. So I'll start a dev stack on the first node. That's my little visualization tool. Let me just go here. Okay. So I'll start my visualization tool polling the API for all 750 nodes that haven't started up yet. I'll start up the first 250. And we can watch those nodes. Okay, so we've got 250 nodes up and running. If you want to verify the nodes, you can see just the data describing those nodes in the network is 2.8 megabytes of JSON data. So that's 250 nodes with 23,000 connections between them. So now we can scroll up and find a libp2p address to peer to. That one will do. And then we can run this with 250 nodes. I think I copied that. Yep, that's right. So I'm just going to copy that. I'm going to run it in parallel across the other 2 nodes. Now we'll be able to see the other 500 nodes that we just launched start to connect. Okay, so now we've got 750 nodes in the cluster. And this is what I lovingly call the blob. It's now so densely connected that it's very slow at rendering, and you kind of can't see the wood for the trees. But you can see this interesting structure that there are some nodes that are like more densely connected than others, which I think is just kind of how libp2p has self-organized here. So let's see, how does the system perform? So we've achieved scale of 750. The system starts, it doesn't crash, and the nodes pair with each other at 750 nodes. Let's see what happens when we submit a job. It works. Okay, so we managed to run a job across 750 nodes. It got scheduled on 3 of them, and we can see that as requested, that execution happened across exactly 3 of the nodes. So the system is functioning to a basic level, yeah, so now I can show you what happens when we run the explode.sh script, which, as it says on the tin, is meant to break things. So let's see what happens. So now this is running 10 jobs at a time at a parallelism of 2, as in 10 jobs, one after another, in each batch. And it's running that thing twice in parallel with itself. So you can see my basement is now warming up. All of the CPUs are pretty pegged. And in fact, I'm already quite concerned about the memory usage. So the memory usage here has shot straight up to 60%, 61%. And I'm going to have to turn this test off pretty quickly if I still want to be able to SSH into my servers without having to go into the basement and reboot them. But we are getting jobs passing. So despite the fact that the system is stressed, we are getting jobs finished within the timeout. The timeout is 30 seconds. But the system is not stable at this scale because the CPU and memory usage is pretty bad. And in fact, in particular, the memory usage just falls off a cliff, and the machines crash. So we know what we need to do next. Performance is next on the track for the work that we're going to do in August. And I hope in August to get this system to the point where it can quite comfortably run 750 nodes across 3 servers and use barely any CPU and barely any memory. But right now, I'm going to kill these ones before they kill my computers. So yeah, that's the end of the demo. Thanks for watching, and I'll put more info on the wiki, on the project report. So great to see everyone. Thanks for watching. Bye.